Continuing 8.2, Introduction to Subsidence and Soil Volume Change. The next type of subsidence we'll discuss is thawing of frozen ground. This is a problem in some areas of Alaska. As permafrost thaws, the ice melts. Water, as you know, expands when it freezes, so when ice melts, there is already a reduction in volume of the soil, causing subsidence. Then, as you know, water also flows and evaporates, and other such stuff that cause the water to leave the soil in an area, which also reduces the soil volume. Now think of all that organic matter that has been preserved in the frozen ground. When the ground is no longer frozen, that organic matter can decay faster, which, you got it, also reduces the soil volume. Let's go through the pictures. In the picture on the bottom left, you can see the dirty white ice exposed under a draping blanket of vegetation, with some vegetation blankets rolled up by the water. The thawed, soggy soil is literally being washed away from underneath the vegetation. The image at the top right shows some slump features caused as the slope is destabilized as the ground thaws. Remember mass wasting? Well, here it is again, associated with the thawing of frozen ground. And the picture on the bottom right shows how inconvenient thawing frozen ground can be. I'm pretty sure that cabin wasn't built that tilted. Subsidence can also be caused by the compaction of sediment. Here is a cartoon of dry and loose soil versus wet and compacted soil, with a very unfortunate house. The dry, loose soil may have been deposited by wind or quickly deposited by water and then dried out. Dust deposits, loess, and stream deposits in arid regions are bound with clay or water-soluble minerals. Water weakens and or dissolves the minerals, which leads to collapse. What type of environments do you think might have dry, wind-blown soil? Did you think of deserts? Me too. Arizona, Nevada, interior Southern California, New Mexico. A subdivision gets built in the desert, and then over irrigation of landscaping vegetation, then soil subsidence and foundation problems. Darn, these soils can be called collapsible soils. Sediment can also be compacted as a very moist soil dries out, as in deltas. Furthermore, as the soil dries out, the soil environment becomes less anoxic and more oxic, i.e. less oxygen to more oxygen. This increases organic matter decay, which further reduces the soil volume, especially in organic-rich soils. You can see the time progression cartoon on this slide. Original pre-1880 conditions of a delta marsh island with anaerobic decay, i.e. decay without oxygen. The soil is very moist and the water table is so high. Vegetation is growing like mad, and the marsh platform is rising. Apparently in the 1900s, a levee was put in with a pump and drain. Perhaps someone didn't like all the mosquitoes in the marshland. Microbial decay of organic matter turns aerobic, i.e. with oxygen, which is much faster than anaerobic decay. The soil compacts as it dries out. There's also some wind erosion. The soil subsidence will result in either increased levee maintenance and pumping or destruction of the delta marsh island. Earthquakes can also cause soil and general ground subsidence. The cartoon at the bottom shows uplift of the land due to stress from the colliding tectonic plates. When the earthquake releases all the tension and stress, the land subsides. The top picture shows land subsidence at Littleton Port of Christchurch, which has already slumped 20 to 30 centimeters following the major earthquake on September 4, 2011. The land could continue sinking for the next 3 years. Drained lava tubes can also collapse, causing a sudden subsidence. Can you see the collapsed lava tube in the picture? Here's a hint. The students are standing in it. Withdrawal of underground fluids has also caused subsidence. Look at the picture. San Joaquin Valley, California. Dry place with lots of agriculture. The water for the agriculture comes from groundwater, stored in sediments hundreds of feet below the surface. As we pump water from the ground in this location, the water pressure in the sediments that formed the aquifer decreased. Part of the water pressure was pushing out on the sediments in the aquifer, keeping the sediments a little more separated from each other than they would be under normal atmospheric pressure. As the water pressure was decreased, the sediments compacted, lowering the land surface, apparently about 30 or so feet in 50 years. If you are still trying to imagine the water pressure thing, think of a balloon. Under normal air pressure, the balloon is just a small floppy thing. There is the same air pressure inside and out of the balloon. Increase the air pressure inside the balloon and it expands. The aquifer slightly expanded as pressurized water filled the subsurface. How did the water get more pressure? Well, that has to do with where the water entered the subsurface. If the water that filled the aquifer entered the subsurface high on a mountain, and the aquifer is confined or sealed off from the surface down in the valley by perhaps an impermeable layer of clay or shale, then down in the valley, it would feel the pressure of where it entered the ground high on the mountain and want to rise as high as the mountain. But it can't rise that high in the valley because the aquifer is sealed. So instead, the water pressure pushes out on all the sediments in the aquifer, and the sediments slightly expand, just like a balloon. But also just like a balloon, when the pressure is released, the sediment volume shrinks. But unlike a balloon, when the pressure is released, the sediments are not floppy rubber, but more compact, and will not be re-inflated. The aquifer is permanently impaired and will never hold as much fluid again. Here's a flawed cartoon to help you picture the compaction of the aquifer as water is withdrawn. It's flawed but still useful. First thing to note is that there must be an impermeable layer. Otherwise, there would be no significant water pressure and definitely not enough water pressure to keep the sediments slightly separated. If there was no impermeable layer, the water would just flow up onto the surface. So I added the impermeable layer. Second, as the aquifer is depressurized, as seen in the bottom half of the cartoon, the aquifer doesn't have to become dewatered. It can in extreme scenarios, but usually the pressure is just decreased as water is pumped out, so the aquifer doesn't dry out. Back to the balloon analogy. Even when the balloon is deflated, there is still air in it. It's just the same air pressure as outside the balloon. In the close-up views of the sediment in the aquifer, you can see how the water pressure originally let the sediment be less compacted, and then when the pressure was reduced, the sediment could compact more, which resulted in subsidence. Now let's get back up closer to the surface. Moisture content in soil affects the shrinking and swelling of clay minerals in the soil, creating expansive soils. I repeat, clay minerals, which is different than clay-sized particles. There is a group of minerals that are called clay minerals. The mineral structure is like a book or a stack of papers. They are pretty flat. In fact, the mineral structure is often called platy. So, these minerals have strong atomic bonds along the flat plates or paper sheets, but very weak bonds between. You may be familiar with a clay mineral called mica, as seen in the image in the middle. They are very common around here. They are shiny and you can pull sheets of the mineral off. After playing in the dirt, small flakes of it seem to stick to my skin, almost like glitter. Do you know what I'm talking about? If you don't, look for it next time you're in the Boise foothills or McCall area. So the weak bonds between the mineral sheets are mostly a polar attraction between the two plates. One side of the plate has a slight positive charge, and the other side of the plate has a slight negative charge. Opposites attract, so the positive side of the mineral sheets are attracted to the negative side of the mineral sheets, and they pile up like a stack of molecule-thick papers. Now, water is also a polar molecule, meaning one side is slightly positively charged, and one side is slightly negatively charged. Can you see how they'd fit right in between the mineral sheets? Now, as water snuggles in between the mineral sheets, the sheets move slightly apart. This is depicted in the cartoon image on the left. The top cartoon is before expansion, the bottom cartoon is after expansion. The blue balls are the water molecules. The tan lines are the clay plates. Now let's zoom out from the molecular level to thinking about the mineral as a whole. As each clay plate expands away from the other clay plates, the mineral on the whole has expanded quite a bit. Some clays expand 10 and 20 times their size in a matter of minutes. Now let's zoom out even further than just minerals. Think of a soil with high clay mineral content. As the soil gets moist, what will happen? The soil will expand. As the soil dries out, what will happen? The soil will shrink. As it expands, you get a popcorn texture, as seen in the right top image. And when it dries, you get drying cracks, as is seen in the bottom right image. This expanding and shrinking can be a doozy for buildings. Do these soil textures look familiar? I have to admit that I see this happening in the soil in my backyard. Expansive soils expand during wet periods and shrink during dry periods, i.e. change in moisture content. After expansion, soils can have cracks and popcorn-like texture. This is common in clay, shale, and clay-rich soil containing smectite and other clay minerals. Have to have the clay minerals for the soil to expand and shrink. The image shows dried out soil that shrank and cracked. Expansive soils often will produce wavy bumps and surfaces, as seen in the image on the top right, causing tilting and cracking of sidewalks, foundations, utility poles, and headstones. The tilting headstones are seen in the bottom right image. The expansion pressure can be greater than 10,000 pounds per feet, which is 500 kilopascals. That's way more pressure than your car tires. The cartoon on the bottom shows how there can be local variation in soil moisture content, and therefore local variations in shrinking and swelling. The tree is drying out the soil because it is thirsty. Well, the house is just sitting on wet soil and is not thirsty at all. So the drier soil by the tree is shrinking while the soil under the house is expanding. Subsidence and soil volume change is also an issue in frost-susceptible soils. These are soils containing water and expand when frozen. It is most apparent in silty soil. Frost heaving causes upward movement of soil particles, and water is drawn into freezing zone. These last two are linked together, and we will talk about it more later. I bet you can't wait. This phenomenon can cause greater than 9% volume increase. For frost heaving to occur, there are three conditions that must be met. 1. Temperature must be below freezing in soil for a long enough time for significant ice to form. 2. Water must be present. And 3. Soil must be permeable, silty, so the water can get into the soil in the first place.